Give me a moment. All right, welcome everyone to the A48 Midterm Review Seminar. I'm Miles. I'm going to be presenting the first third-ish of the seminar, and yeah, hope you guys are studying for the midterm. And yeah, so we've more or less break this down into 3 sections. So kind of just more like general C syntax, memory model, and then we're going to do some stuff on linked lists as well. So this isn't like a full list of everything to study, I believe. There's some kind of other topics that we've kind of crammed in there as well. I know like complexity, for example, is also going to be on your midterm, and that's going to go with, that's kind of mentioned a little bit later, but yeah, so I guess we can just get started. So starting off with syntax. So first off, we're just going to do just a little bit of review with arrays. So kind of one thing that's maybe, actually here. So can you have multiple different data types in one array? No, I'm seeing a lot of no's. So that's right, so there's only one possible data type. So this is obviously different from Python, which you probably did in A08. So all the elements in an array have to be of just one data type. And then next up is we have this piece of code. And so I guess I should kind of rephrase it as, is there anything wrong with this piece of code? And if there is, what is it? Yep.
Well, what's wrong is that we're at, well, I was about to say we're using double quotations, but that's fine. We're creating a string.
Yeah. So I guess, yeah, so double quotations is actually fine there because we're defining a string. Yep. So kind of. So that's almost it. Yep. Sorry? Exactly. So kind of what you said over there, that there's no \0. So we are allowed to define a string like this without explicitly having that \0. But in this case, we can't, we don't actually have enough space in our character array to store it, since our character array is only containing 5 characters. And to store something like this in C, we actually need 6 characters. And so that's kind of what I wrote, is that there's no space for the null terminator. I'm pretty sure, I actually haven't tested this in C, that this would still be stored as an array of characters. But if you were to try to display this as a string in C, then we would get some sort of error. I haven't actually double checked that. I think someone can probably run that code and double check it for me. But yeah, all right, moving on. Next up, we're just going to do also a quick review of some pointers. And so kind of a very basic questions. So what do pointers hold? Like what data does pointers hold? Yeah? Yeah, yeah, so it contains the memory address of another variable, right? So moving on. And so this one, I'll give you guys maybe a little bit of time to think about it, but what is the output of the following code? Oh, sorry, that should say, what is the value of A and B there? I think I maybe modified this one a bit, so kind of what is the value of A and B in this scenario? Yeah? 10 and, so which one's 10 and which one's 6? So that's exactly right. So it's going to be 10 and 6 because we have the first one is the pointer to the start of the array. And so we're actually pointing to the next one. And the second one is just going to be the value at the start of the array plus 1, which is going to be 6. So that's the answer. I guess I should say 10, yeah, 10, 6. I guess I formatted it a little bit differently in a previous version of the question. But yeah, it should be that A is 10 and B is 6. And then finally, is there anything wrong with this code? And I guess, what is wrong with this code? That's the hint. There is something wrong with this code. Yeah? Not quite. So, yeah, are there anyone else? Yeah?
We freed the location that B is pointing to, but then we assigned it to another value, which doesn't work.
So that's exactly right. So typically what we're doing with pointers is that we are kind of allocating our own memory. But this kind of everything up to that last line is actually allowed. But what we're doing is when we free B, the variable B still exists, but but since B is pointing to A, what we're doing is essentially deallocating A. And so when C tries to write to A, it doesn't know what to do because it's already deallocated that memory. So A no longer exists, so that's going to just throw an error. And so yeah, as I said, free B deallocates A, but accessing A, again, throws an error. That's good with everyone? All right. All right, so now we're kind of getting into more of maybe questions you might see on a midterm. So this is kind of more of just like a setup. So for this example, or I guess the next couple of examples, we're going to be kind of dealing with a toy example of a chat room. And so here the two structs that I have are, I have one struct to kind of, or I guess the idea is that we want to represent data of a chat room, right? So we want to be able to have multiple users and maybe kind of messages that those users would send. And so the first struct is just going to be kind of the author ID, which I've just set as a random integer. And a message, we'll just say that's a max length of 256. And then the chat room is going to contain a couple user IDs, which just shows kind of who is in the chat room. And we have also, we're storing the messages, and we're storing them kind of notably as pointers. And I'll kind of get to why in a second. And we can store up to 100 messages in this chat room. And so I guess kind of one motivation for that is, think about this for a second, but we have kind of two variables A and B, which are very similar. The only difference is in A, we're storing an array of 100 chat structs. And in B, we're storing the pointer to 100 chat structs. And so I'll give you guys maybe like 30 seconds to think about kind of the answer to this. But yeah. So is A or B going to be bigger? Or are they the same? So does it actually matter whether or not we store a pointer? All right, so I guess hands up if you think it's A, or I guess, sorry, if you think it's 1, if A is greater than B. Seeing a couple hands. And then, so I guess hands up if you think B is greater than A. Also a couple hands. Hands up if you think that A and B are the same. Okay. And I guess raise your hand if you don't think we have enough info. Okay. So kind of mixed, a little bit unsure. So I guess, does anyone want to explain why they think A is less than B? Yeah?
I want to explain vice versa. Why?
Oh, sure. Then, yeah, you can explain why A is.
Basically, because for the B, we point to an array, and when we point to array, we point to the primary cell of this element.
Right. Yeah. So you're just pointing to the start of the array, right? Versus in the chat, in the first one, we're pointing to the whole array. So that's not quite it, because when we're dealing with lists, or sorry, this is not Python. When we're dealing with arrays, we actually kind of, the variable A actually references the start of the array anyways. But so I guess for a little bit of context, when we run this size of function in C, it gives us the size of the whole array. So yeah, are there any other thoughts? Yeah?
The second one, the pointers already have a fixed size. So the size of the pointer will be the formula by 100. But for message 1, it have like a MSG 256 and char, like each side of char is 1. So like for the worst case, it have like it should be bigger than.
So yeah, that's exactly right. So when we store an array of pointers, what we're storing is memory addresses, right? So typically for your computers, that would be, because they're 64-bit systems, so that would be 8 bytes for every pointer. And so when we store this message, it's going to be 8 bytes times 100, and that's going to be the size of that, the size of that array. But when we're storing the A, so when we're dealing with the with an array of the struct itself, then we have to store the entire struct. So we have to store the entire possible message for every single message. So what ends up happening is the A ends up being a lot bigger than B, because we have to allocate space for all the possible room that a message could take up, versus B, where we can dynamically allocate space for each chat that we end up using. So yeah, so A ends up being greater than B, and yeah. Are there any questions about that before I move on? Yeah?
Sorry, could you just quickly go over again why A is larger than B? I get what the size of B, how you calculate the size of B, but
sure.
how you calculate the size of A.
So the size of A, so if we were to run size of chat, we would get, it should be 256, because that's how big our character array is, plus integer is going to be another 4 bytes. So if we run size of chat, it should be 260. I know there's something in C where it might not be exactly 260, but the point is that it's going to be, in either case, greater than if we were to run size of a pointer, which is always going to be 8 bytes, or 4 bytes if you're doing a 32-bit system, but you don't really have to worry about that, I don't think. But in either case, storing a pointer is going to require far less storage than storing the actual struct itself. Yeah, so the fact that it's an array is a little bit of, I don't want to say a trick, but it's kind of a little bit distracting to the actual reason why these have different sizes, is that a pointer takes less space to store than the actual struct itself, because we're just storing where that struct is stored. We're not storing the actual struct itself. All right. Yep.
So for B, is it 8 because it's 8 bytes, or is it 8 times 100?
8 times 100. Sorry, I should have made that maybe a little bit clearer. So that's 8 for each element in the array. So if you were to, yeah, so the size of kind of any individual pointer should be 8. Again, I'll have to double check that because I'm a little bit flaky on the C syntax, but yeah, so that's kind of the reason why. All right, I think I'm going to move on. If there's more questions later, you can come up to, I guess, any of us after the review seminar. But yeah, I think we should move on. All right, and so next up is kind of just maybe a little bit easier of an example. This is definitely something that comes up on a lot of midterms, is kind of you get a struct like this, and you're kind of asked to create an example object, or no, I shouldn't say object because that's not technically the right term, but an example, let's say, just say chat room that contains certain data. And so, again, I'll give you guys a minute to think about this, but yeah. Yeah, and then one other thing I should mention is it's not in the kind of big code where the answer is going to be, but kind of just imagine that there's a big include string h, because I guess, yeah, a bit of a hint. We are going to be using at least one function from string.h because we're dealing with strings. Yep.
User ID's length, the variable there, is that just how many users there's going to be within the chat room?
Yeah. So someone had a good question. So again, maybe should have clarified this a bit. I have it on my screen. I don't know why I keep looking at that. So the user's ID length and the messages length fields, what those fields refer to are how many users are currently in the chat room and how many messages have been sent in the chat room. And the reason we have to do that is because we've already pre-allocated all this space for our chat, users and our messages, we don't actually know how long either of those arrays are. So we have to have a separate variable to manually keep track of that. Actually, the very next question we do use, I think both of them actually. So yeah. All right, I'll give you guys, how are we feeling? Like, good, okay, I think I'm just gonna go over it. So the first thing that we wanna do with a question like this is we just wanna create new, like a new chat and a new chat room. So here we only have one chat room and one chat. So, oh, whoops, sorry. It is here, yeah. So we just can create a new chat and new chat room. I just gave those variables. If you're writing this down on your own, obviously the variable names could be different and it would still be fine. And so what I'm just gonna do first is create the new chat. And so I'm just going to give them the author ID of 42. And for the string, we can't just assign a string like we would in Python. We can't just say new chat.message is equal to hello world, right? We have to use those string functions because of how C deals with strings and because they're actually character arrays, right? So we can use the string copy, or I think strcpy. So we can use that function to kind of allocate that hello world message to the new chat struct. And so now we have our chat struct, and so we can move on to our chat room. And so for this, for the user IDs, I kind of just set them very similarly to how I set the author ID. So that's just taking the chat room.user IDs and manually setting the array, so the first element in the array to 42 and the first element to 43. And then we're also updating the user ID's length because, again, if we were to maybe add or remove a user, then we want to be able to know how long our array is so that we're not removing important information or we're not adding or not reading any garbage memory that might already be in that array, right? And then lastly, we want to add the message that says, one second. Oh, sorry, yeah, I got lost for a second. So lastly, we want to add to the messages array in the chat room. And we want to do that with the new chat struct that we already created, right? And so here, because we're dealing with an array, we want to go to the first item we're assuming that our messages array is already empty because we've just created this. But we're going to the first item in our messages array, and we want to set it equal to the memory address of the chat struct. So we can use the I think it's an ampersand, the and symbol to symbolize that it's the memory address of it. If we weren't to include that, then I think it would just throw an error. At the very least, we would get some bugs, but I'm pretty sure it would throw some sort of error. And finally, we want to just set the messages length to 1, because we have 1 message in our current chat room. Yeah, I'll let you guys take a picture. I guess, are there any questions before I move on? All right. See some people taking pictures. I'm going to move on, though. Again, during the break, if you missed any of these slides, you can kind of come back and you can take some more pictures. The slides, I forget. There's going to be a recording, so the slides might be uploaded as well. I'll have to double check that, though. All right, anyways, moving on. We have kind of one more question about this. So this time, we're going to be writing a function instead. And so for this, we're going to be taking in we're going to be adding a new user to the chat room. And so the 2 fields are kind of the new user ID, and we want to pass in the chat room itself. And then we don't actually want to return the chat room. We want to return kind of like a status. So we want to return 1 if the chat room is already full, or we want to return 0 if the user was successfully added, there was enough room for him to join. And again, I guess same as last time, I'll give you guys a couple minutes to think about how you might do this. One thing I will note just to note is that the chat room parameter in the function is a pointer. So just thinking about how that might affect the syntax of your code. All right. We're making good time. Oh, whoops, did not mean to do that. There we go. All right, I'm going to take this up. OK, so all right, so does anyone have an idea of what we might do first? Yep.
Like check if the user ID's length is 20, then return 1.
Exactly. Yep. So I essentially have that exact code on my screen. And in terms of the actual syntax, give me a second. We have if chat room arrow user's ID length is greater or equal to 20. If you put equal to 20, that works just as well. Then we're going to return 1. And then one thing I'm just going to note here is, again, because we're dealing with a chat room pointer and not the actual data itself, we're going to be using that arrow instead of the dot. So kind of for this last question, we used the dot when we were referring to the struct itself. But when we're dealing with pointers, we want to be using the arrow instead. Right. And then does anyone kind of have any ideas what to do next? Yep.
Okay, so we will assign the chat room first. We will assign the chat room that user ID length to be the new user ID, and then we will add length by one.
I think that's what you were saying. So we have our chat room user IDs, and kind of where that length comes in handy is that we're able to use that to determine where in the array we should write to. So I could have broken this down maybe one step further to create a variable just to get the current index. Current index. But I just kind of did this in one line. Both methods are perfectly fine. Actually, if you were to use a separate variable, the code might look a little bit cleaner. And so we're just setting that address in memory to the new user ID. And again, in both cases, we're using an arrow because, again, we have a chat room pointer instead of just using a chat room itself. And then we're also adding the user length afterwards, because if we were to call this function again, we want to make sure that we're adding the new user to the right part of the array. And you can even kind of think about what a delete user function might look like. And actually, we don't even have to deallocate anything. All we have to do is just subtract the length by 1, because that way we know, our code knows to not look at any information past that point. We assume it's garbage anyways. So yeah, that's kind of one of the nice things about C, is it makes some code like that a lot nicer to deal with. And then we return 0 at the end, because our function has to return 0. Yeah?
Sorry, maybe I just misread it, but it says if a chat room is full, it doesn't say already full. So wouldn't we want to do something different, like in terms of the structure? Or, because if I'm understanding the code correctly, that's just checking outright if the thing's already full, right?
Yeah. So we're here, we want to check if the chat room is full because we might be dealing with a full chat room already. There's nothing in our struct to specifically say, if the list is full, then we're not adding. This is the function that's adding that user, right? Yeah, so yeah, that's kind of, you have to like rewire your brain a little bit from Python, where Python, I have these lists and they can store infinite numbers and they're a lot easier to deal with. But in C, we have to be very precise about what we're storing. All right, are there any other questions about this? All right, I think I'll move on. I think this is it for C syntax. All right, yep. So I guess it'll be a little bit of a break anyways, because we got to switch over the mics. But yeah, I guess if you have any other questions, you can come up to me, I guess now, while I'm switching over the mics. But yeah. Okay, I think I should mute this. All right.
Let's continue on with the seminar. In this topic, I'm going to be talking about memory models. So it's similar to the Python memory models that you learned in A08, but with a bit more complexity added to it with pointers, memory addresses, and all. So on the screen, you see the basic definition of what a memory model is. A memory model is an abstract representation of how the memory is organized and accessed by the program. It describes three main things: how variables are stored in memory, how memory is allocated and deallocated, and how the program interacts with the memory during its execution. And I can guarantee you that in the midterm, you're going to have one question for at least 20 marks or something about memory models, right? So let's start off with an example. Here's an example with a function call. And the first statement includes bringing in the library, like the standard library for C. I define a function square that takes a parameter of integer x, has an integer x, I do some multiplication and return a value. In the main function, I initialize two variables, input and result of type integer. And I assign the value 7 to input, and I call the function square. Now I'm going to give you guys a few minutes to draw the memory model and get back to me. So let's start. What return statement?
Return int, return 0 int.
Let's ignore that. Let's ignore that. Yep.
Since there isn't a return statement in main, should we just not include that in the memory model?
No, try to include the return statement even though it's not given in the main one. Think of it as an explicit return statement. Yep.
Where do we exactly
Well, you can think of it as, let's assume that in the exam, the professor gives you a memory model with numbers and memory addresses. But if you're drawing it from scratch, you can just allocate a box, name it a random number, assume that's the memory address, and then follow from there. Allocate, add how many ever boxes you need, and keep continuing on. That's pretty much it.
Yeah, but which line do we?
So let's think how a program executes. It starts from the main function, right?
Yeah.
So you go line by line from input, result, and then go to the function.
Yeah.
Is that your question, or?
No, my question is like, do we draw it at the very end after everything happens? The memory model?
Draw at the very end.
Like after completion of line.
Of the completion of yeah. For now, yeah, do it till the completion of the program. It's not a long code, right? So it should be. I think in the exam, if there is like a 30 or 50 line code given to you, which I don't think is possible because it takes time to do all that, they would say do it up until line something. But in this case, do it until you get a return value from square and show what is in the memory at that point. Did you get it right? Okay.
Now, I know this was probably answered before in the class, but obviously when you're finished using square, it deallocates all
Right.
the memory. But I'm assuming we want to include it in the memory just for like knowing what we're doing, knowing what we assign to what variable.
Yes.
Right?
Just as if you want to like be more explicit, you can like draw an X over here to show it's deallocated, but it's still there in memory kind of thing. Okay, so let's get on with the answer. I feel like everybody's done. It's a small code. Here I have 4 boxes for the memory model. I'm going to assign them random numbers. So let's just say the memory address for the first box is, let's say, 1111. I'll just do over here 1111. This is going to be 1112, 1113, 1114. And the first line of code tells me that I have to initialize or declare a variable of type integer called input. So I'm just going to call this input of type int, right? And then next, I do the same thing, but with another variable called result. Result, type int. And next, we assign a value 7 to input, which is 7. So input is going to have the value 7. Then I'm going to call the function square and passing in the parameter input, which is of 7. So I'm going to allocate or draw more boxes for the square function. Let's just do this. This whole thing is reserved for main. This is going to be for square. So within my square function, I have an input parameter x. So my first box is going to be dedicated to x of type integer, right? And then that value is going to be 7 because we're passing in input, which holds the value 7. So let's just call this box 115 holds 7. Then I create another variable s within my square function. So this is s of type integer. And that holds nothing for now. And then it has a return box for s. So this is going to be my return. And this is going to be of type integer. Right? So the first operation that I'm going to do within the square is multiply x times x, which is 7 times 7, which is 49. Then I'm going to return this value, 49, back to the original main function. And it's going to be stored in result. So this is going to go over here to 49. And then, so in an examination hall, you may have 2 questions. Let's assume that in this question, I tell you to execute up until the line result. And you may ask the TA, am I supposed to erase everything that was within my square function? And the TA may give you 2 options. One, you go ahead and do it. Or if you're unsure and you want to display as much information to your TA while grading to show that you actually done the work and you have the correct memory addresses and stuff, just probably, I don't know, like probably draw a light line to show that this whole memory part was deallocated after it returns the value s, just to be 100% clear with the TA. So after this value was returned, everything within my square function is gone. So that's why I drew a line. And then there is no return statement, but let's just assume there's an implicit one, which is going to return. So since everything was working out fine, I'm just going to return value 0 to say everything is A-OK. All right? And if you have extra memory boxes in your memory model, make sure to say empty, because even if we reserve this entire space, we want to say that in this box, we do not know what's there. It could be junk. We don't care about it. But for the simplicity's sake, it's empty. Yep?
So if we have a scenario like this where we don't have an explicit return statement, we just assume that it would be the variable or element inside of it 0?
This one?
The return.
This one? Well, you can leave it as this and say empty as well. But it's better to show that you have a return statement, or else you're going to be probably dogged a mark for that. OK, is everyone clear with this? Yes? Without the function call or with the function call? Yes. Well, if I were to be writing a midterm and they say execute until the function call, I would draw all this and probably draw a line to say I've done my work. Here's my work. But since the function returns a value, this whole memory block is no longer there in the computer. Well, I just wanted to name the example call with the function call. There are other examples with pointers and such, so I just wanted to name the thing. OK, let's move on to the next question. So the next question is also a memory model with pointers. I'm going to give you guys 5 minutes to come up with a quick memory model for this one. Yep.
Could I also just write down that like everything is like deallocated, like on the side?
Yes, you could.
Okay.
Yep.
But if it was right, then we don't need to stop.
Am I misread it like this, like return like 0 like that?
Well, you could do an implicit 0 for the thing, but you could also just have return to be empty.
Oh, so
because
I can just not have this here.
Yeah, just make sure you say that it's empty, because we don't know what's in this box, right?
Oh, right. If it's wrong, it's not 0.
Because you didn't return anything from the main function, but you know that there is a box allocated to the return function, a return statement, right? Yes.
Okay, thank you.
So, is everybody done with the memory model? Thumbs up? Okay, so let's get on with this one. Okay, let's see. Okay, so this function is fairly straightforward. Has the first line saying that I'm going to be initializing or declaring two variables, x and y of type integer. So in my box, I'm going to have x, and then of type int. And the next one is also going to be of type int called y. And then in the next one, I declare a variable, p, and holds the value null. So in this one, I'm going to do this. NULL null. I'll point it to an integer, p, right? In the next line, I assign the value 5 to x. So in my box for x, I put 5. And then for p, I'm going to be storing the address of x. So instead of null, this is going to now hold the value 1, 1, 1, 1, right? Next one. We use the memory address and store the value 3. Yes?
On the test, since p was null before, do we cross out null and then write the memory address?
You could do either way. You can either erase it. Sometimes they only want to look at the final answer. So yeah. So since p holds the address for x, we're going to use this address and store the value 3 in x. This star basically denotes that whatever contents is stored in this box or through this address, you just go and change that, or you store a new value. So in this case, I want to store 3 wherever this address is pointing to, which is box x, right? So instead of 5, I'm going to erase 5, store 3. Then in the next line, I take the contents of p, which is 1, 1, 1, 1, 1, referring to x, and store it in y. So in my box y, I'm going to be storing the value 3. Did everybody get that? Awesome. Okay. Yep.
And I'm assuming return statement.
Oh yes, the return statement as well. Return empty. Got it? Okay, next example. So this one is a combination of the above two examples. We're going to be using pointers and a function to get the value.
exam, are they going to tell us at what point they want us to draw the memory model?
Yes, yes. Since these examples are just like two small functions, just assuming that you would go through the entire thing, have the function calls and all.
Like for example, like for this example, tell us that like before, because the square function after it's executed, it just like the memory that it holds is clear.
It's gone, yeah.
So it would tell us like, oh, like we're at this point. Right?
Yes. And if the question is not clear, just be sure to ask the TA because they would know. Yep. Do you guys need more time to complete the memory model, or are you guys done? You're done? Okay, let's continue on with the answer. So, similar to the first example, we're going to initialize a variable called myInt of type integer. So in this one, it's going to be myInt, and then this is of type integer. In the next line, we assign the value 7. And then we call our function. In our function, we're passing the address of the integer box, myInt, which is 11111 in this case. So I have a box in my square function. And let's say this memory address is 1115, holds something called p. The type is pointer to an integer. And it gets the value 11111. OK, so now we're in this function. In this function, we create a variable called x of type integer. So let's have another box for x. X of type integer. And then we take the contents of p and store it in x. So p is basically pointing to myInt. It's storing 7. So I'm going to take this and store it in x. That's what the star means before the pointer. Then within x itself, I multiply 7 times 7. So this becomes 49. Let's say this box value is 1116. And then we take whatever is in x and go to the contents of p. So p is storing the box or the memory address for x. We go over here and take whatever is stored in x and put it over here. So this is basically taking whatever is here to here. That's what this statement does, right? And there is no return statement because it's a void function, so it doesn't return anything. So let's close off this function over here. And then in the main function, I'm going to have on the console or your terminal, you're going to have the final value of for myInt is, and you get the value. So this is going to be empty. Oh, this doesn't even exist. Empty. There's nothing there. And that's pretty much it. Did everybody get the same memory model? Thumbs up? Yes? Yes. Here? Well, since there's nothing over here saying I'm returning 0, if you want to stay true to the code and assume you have an explicit return, just leave it as empty, because we don't know what is being stored there or what is happening in this box. But I believe the professor wants you to have an implicit return statement in your memory model. But if you're not returning anything, just leave it as empty. I think the TA will understand that. And in your void function, if you want to include a return statement, the return statement is going to be after the line the star p equals x. In the next line, it's just going to have return colon. So it doesn't return anything, but it's just for users to understand that the function is done. It returned nothing, basically. Yep.
If we do say that the return is 0, is that wrong? Or is
It's technically not wrong, because it's just saying that the function ran correctly, and 0 in C is like true. So it's like signal green. The function had no problems. But I would suggest stick to empty, because you don't want to confuse the TA, right? And it's not really returning 0 in this case. So does anybody have any other questions regarding memory models? Yes. This one? This is not an array. Sorry, this was just meant to say this whole thing belongs to square function. Yes, because since it's escaping the function, like the function scope, it's gone from the memory. So yeah, if you draw a line, that's just more complete. Yes. Print? Well, print works in a different manner. It doesn't really allocate anything, and it's directly talking to your terminal. Well, there's like other background stuff that is happening to print something, but you don't really need a memory box just for print, because you're not storing anything. This gets outputted on the terminal, right? And it's not storing anything, so you don't have to store anything in your memory model. Yep. Does anyone have any other questions? Yep. Pardon? Repeat the question again.
Like square function call.
Uh-huh.
Why don't we have it showing up in our main?
Well, we're not really storing anything for square, right? We're just calling the function. And when a function call happens, you know how in Python you have, if you were doing memory models, I believe, which you did, it would have like a function scope. So these 4 boxes in my diagram refer to the function main. And once I call the function square, I create 2 boxes in my case, and I allocate it just for square. Anything that happens here is within the scope of square and does not affect main. And if my square function returns something, or in this case is changing the contents using a pointer, then only it's affecting these 2 scopes. So this whole thing is independent of what's happening here until a return statement or a pointer affects that. So you don't have to store the square function in a box, because there's no variable holding the square function, right? It's just being called. So you create these 2 boxes. Is that clear? OK. Any more questions for memory models? I think it is pretty clear that memory models are straightforward if you understand C syntax. And let's move on to the next slide. All right, so in this topic, we're going to be talking about linked lists. Prithvi is going to take over from here. There's a lot of mics you got to put on. You hold this one. This is the speakers that's happening here, and this one is the recording that's happening over there. Here you go. So just click the buttons, and you're going to be controlling that screen. Okay. I'm pretty sure you don't need this one, like this one. If you do, just move the pointer to the left side, and you come over here and click. Okay.
Check. Check. Do you need to on something? This?
I think it's already turned on. Yeah, it's already turned on.
Check. Okay. Check. Oh. Where is it?
That one, the red button.
Oh. Okay. Check. Okay. Okay. Okay, so we will start linked lists now. So we will start talking about the advantages and disadvantages of using linked lists as opposed to something like arrays. So let's start off with the first advantage. Linked lists are dynamic. They can grow and shrink without bound. So when we, for example, let's say we set an array. So when we declare this array x with size 1024, but let's say, for example, we use up all the elements here. So we use up all the space for this array. We cannot add more elements. And if we need to add more nodes or more elements to this array, we have to set up a new array. In a linked list, we can just add elements. And if we want to delete elements, we can't do that in an array, but we can do it in a linked list. Now, linked lists utilize memory efficiently. Since nodes are created by demand, space will never be wasted. So if we set, for example, char x is equivalent to, hello, we still have 1018 more boxes of memory that we can use for this array. And we're essentially wasting 1018 boxes for a variable that only needs six boxes. With a linked list, it will only use memory up until it needs. So, yeah. Now, disadvantages. So, in a linked list, operations are pretty slow. So, in a worst case scenario in a linked list, when we add a node, we will have to traverse all the way up until the tail. In that case, that will be on. Similarly with delete and traversing the entire linked list, it will be on. In an array, for example, accessing the ith element is O1. But in a linked list, we will have to traverse until we reach the ith node. And that would be on. So now we will talk about dynamic memory allocation. Oh, okay. Yeah. So in dynamic memory allocation, when inserting nodes to a linked list, we can create nodes on demand, as linked lists are flexible and can grow and shrink continuously. So there are two methods used to allocate dynamic memory. The first one is calloc. So calloc takes two arguments. The first argument being the number of elements that we want to allocate, and the second argument is the size of the element that we are allocating in bytes. Also, when using calloc, we initialize the allocated boxes by setting all elements to 0. Now, with malloc, it will just take one argument, which is just the number of bytes to allocate. Unlike calloc, malloc does not initialize allocated memory. So whenever we allocate memory using malloc, it will not initialize it to any set number. So calloc will initialize it to 0. Malloc, it might still contain junk within the boxes allocated. So can anyone tell me when is it more useful to use calloc instead of malloc, and the converse, when it's more useful to use malloc instead of calloc? Yeah? Yeah, so when using calloc, if we want to say, for example, use a matrix, it's better to just use calloc because we're always going to set each member of a matrix to 0. So that's a better example when to use calloc. Can anyone else think of any more advantages of using malloc instead of calloc, for example? Anyone else? Okay. Okay, yeah? Using words? Okay. I'm not too sure about that. So, yeah? Yes. So malloc is when we're allocating a large number of boxes, malloc will be significantly faster than calloc. The reason why is because, as mentioned, calloc, when we set up boxes to dynamically allocate, with calloc, we reset all of these to 0. So depending on the size or the number of elements we're dynamically allocating, we would have to go through each node that we're allocating and set it to 0. But with malloc, we just leave it be. So does anyone have any questions about malloc and calloc? No? Okay. So now, when we want to deallocate memory, we would have to use free. So free deallocates reserved memory when it's no longer needed. In practice, we should always use free when we dynamically allocate memory, because free would, when a program terminates, the dynamically allocated memory still remains. And this could cause memory leaks. So to avoid this, it's better to use free for any type of variable that we dynamically allocated with. Yeah?
And what would you say are the consequences of memory leak again? Like, how bad would it affect your code?
The thing with, when we terminate a program and we leave dynamically allocated memory, it could cause bugs, because what happens is that if we're using the same memory box in a new program, it will still contain the previous junk as before from the prior program. Yeah. Okay, so let me just. Okay, so now we'll talk about initializing nodes. So in this code snippet, I have a compound data type that is a struct box which contains 2 fields, one of them being a char array or a string of length 1024 and a integer value that is labeled as number. We will also have another compound data type, which is our linked list nodes, that containing one box variable, value, and the pointer to the next element in the linked list. So below, I have a function that initializes linked list nodes for type LL node. So we will see how this looks like in memory at the end of return new node. So at the end of this, you'll see how this looks like in memory. So in this memory model, we have our main function, which has here p, which is initially set as null. This is type LL pointer, our return value. And we also have our function new LL node. This contains local variables in this function, which include new node, new node, and our return value for this function. So what happens here is that in this line, when we calloc, we set a box outside of this memory, which is called the heap, and we dynamically allocate this box here. Oh, oops. So let's check the next line. If new node equals null. So the point of this line here is in a scenario where we cannot dynamically allocate any memory, there is no more space left. In that case, calloc fails. So this will return null in this line here. This line will become new node equals null. In that case, our initialization fails, so we return null. Now we initialize new node. So based on the values that we had here, we copy down the string value, which is CSCA48, and the number value, which is 2024. And our next element we set as null. So the next of LL node is null. And then we return new node. So as we can see, this is what happens in memory. This stores the box that is dynamically allocated, 400, that's the memory address. And the value contains the string CSCA48 and the number 2024. And at the end, we're returning 400, the dynamically allocated memory. So when this program terminates, right before it terminates actually, we release the new LL node function. So this gets released. And this value gets returned back to the value p. So now p stores the memory address 400. And our return value is 0, signifying our program executed correctly. So does anyone have any questions about this part? Yes? Yes, so you're talking about this line here? Okay, yeah, so if you're asked a question to initialize memory on your midterm, include this line here in case calloc fails. Because I know we had a question on previous midterms where if you did not write this down this line, marks would be deducted. So in case calloc fails, or malloc, if you use that, fails, like there's no memory left to allocate, dynamically allocate, check if it equals null, and we will return null. This signifies that our initialization process failed. Yes?
What if we just return new node?
Sorry?
What if we just return the pointer?
Yeah, that works, because new node is null at that time. Okay. Yeah. Yeah? Sorry? What would cause calloc and malloc to fail is if there's no more memory left to allocate. So suppose that we use up all of our memory boxes from another piece of program. In that case, we cannot dynamically allocate from anything because all the other memory is used. So this will return null. Okay, does that make sense? Okay, any other questions? No? Okay. Okay, so now I have a little exercise for inserting delete nodes. So we're going to modify insert a little bit. So this implementation, if we're inserting nothing to the linked list or the length is negative, nothing changes to the linked list. If the length exceeds the size of the list, nothing happens to the list either, and we print out a statement saying length exceeds the size of the list. Otherwise, the node will be inserted so that the index is at its length. So what that means is that if we have a linked list, for example, containing the values 1, 2, 3, and 4, so the head being 1 and the tail being 4, and we do this new type of insert. And this time we're inserting a node, well, the head is still 1, the node being a new node with 5, and we're inserting it at index 2. The new index 2 to this list will become 1, 2, and now this will be 5 instead of 3. And then we start pointing at 3 continuously. And yeah. So this is the structure of the node we're using. It contains only the integer value as its field and the pointer to the next value. And the function that I want you guys to implement is insert len. It has 3 arguments: head of the linked list, the new node that we're inserting, and the length that we want to put it as its index. So I'll give you guys a few minutes to try to think about how you would implement this, and I'll answer any questions in the meantime. Yes. Shall we? Insert?
Assert for like sample checks.
Assert?
Yeah, like if one of our parameters were no, then it will like exit the program and return no.
Oh, exit. Yeah. Yeah, you can use that. For programs, yeah. Okay, so I'll take it up now. Do you guys want more time? Yeah, I heard yes. Okay. Okay, so I'll take up the solution now. Okay, so in our insert len function, you'll start off by declaring and initializing two LL pointers and set them to null. Then you'll start off with the base cases. So it's said before that if we're inserting nothing or the length is negative, nothing changes. So in that case, if new node equals null, so if the node we're inserting is just a null, or if the length is negative, we just return the head back. Now, we check if length is 0. So if length is 0, that's the same as inserting the node to the head of the linked list. In that case, we just set new node and the pointer to the next element to be equivalent to head. And we return new node. So the new head of this linked list will become new node. And it will point to the previous head. This is the exact same as inserting its head when length is 0. Okay. So now we will the code for inserting at other lengths. So we declare p equals head, and we decrease length by 1. So before we go to a while loop, can anyone make a guess or an answer as to why I subtracted length once before the while loop instead of just not ignoring this and just keeping length minus continue here? Yeah.
That's because if you use the data, you have already added one more to it, right?
Yeah, so I think you said the right thing. So when we're inserting at the index, another way to look at it is this is the 0th index, this is 1, and this is 2. So when we're inserting the node 5, and we want to insert it in a way such that 5 will become of index 2, and we'll keep it here, is this originally, before we do the while loop, length is 2 here. So let me just put this as a square to signify the length. So we want to keep it in a way such that it will reach this spot here. So if we traverse it once, it will become, length will become 1 here when we do length minus minus. And if we do length minus minus again, we get 0. And there we insert our 5 when it reaches here. So since we already checked when length is 0, if we insert it or not, if we reach this part of the code, that means length is not 0. So we're already at this part of the code here when we reach p equals head. So we just want to subtract length once. So when we reach 0, we insert it at the correct spot. Does that make sense? Any questions about that? Okay, I don't see any hands up. So we will go inside the while loop now. So using the same logic, we keep on traversing. So we'll keep on traversing until length is 0. So we keep subtracting length, and we keep traversing the list by doing p equals p arrow next. The moment length becomes 0, so when length is 0, it will become here. You would have p being the node q, and then q equals p dot next. So q is 3. And to insert the node with element 5, we just do p arrow next equals the new node. New node arrow next is our q. And we are finished inserting 5 here. And in that case, we just return head. So now the final case is if this while loop terminates and we're still in this function. That means we haven't returned anything yet. In this case, the length exceeds the size of the list. The reason why is because we know length, after all this iteration, after the while loop, if we reach the final 2 lines here, length is greater than 0. If it wasn't greater than 0, if length was 0 at some point in the iteration, we would have met this if condition. At least we would have met this if condition and then returned it. So that means we traverse the entire list, but length is still a positive number, which means length is greater than the number of nodes that are on the list. So that would mean length exceeds the size of the list. So we print this and we return head. So any questions regarding insert here? Anything at all? Okay. So delete, in the same way, delete is very similar to insert in this case. It uses almost the exact same logic, but instead of just inserting an element here, what happens is once we reach our target node, we keep a pre-pointer. So for example, if we wanted to delete 3 here, we would have our pre-pointer at 2, and then our post-pointer at 4. So yeah, our pre-pointer at 2. And if pre-arrow next is equivalent to our target, so we're deleting the node 3, then we point to the target's next node, so 4. So in this case, what happens is pre-arrow next will become 4, and we deallocate the node at 3. So we free Q here. We free Q here, and return head. I didn't go much in depth in here because you guys have seen this in your assignment or lecture notes. And in the same way, this is very similar to insert, where we keep on traversing until we get our desired target. So, yeah. Yes?
When we are freeing something, should we also set it to null after freeing it?
Set what to null?
Whatever we free.
Whatever we print. Target. Well, we're printing just an integer value here, and that integer value is not dynamically allocated.
No, I don't mean for now.
Oh.
In general, do we set it to null if we are freeing something after freeing?
Can you give me an example of like a variable in this?
Like for example, if you're freeing Q, then should we set it to null after freeing it?
Well, Q here is also not a dynamically allocated memory. So once the function is completed, when it returns a value, the computer will release the memory once the function is completed. Okay, so we will now move on to time complexity. So the first question here is, does big O measure the exact amount of operations an algorithm will perform? So can anyone, is it true or false? Can anyone take a guess? It's a 50-50. Yes? No, it won't. Because big O only tells us how much time the algorithm takes as the input size increases. It acts as an asymptotic graph behavior. So when input grows, the amount of it will estimate the amount of time the algorithm takes. Okay, so the next question. Can O of 3n squared plus 2n plus 6 be simplified? So, yeah? Yes, correct. Because as n goes into infinity, n squared grows much larger than n, or a constant. So we can essentially ignore the 2n plus 6. And in time complexity, constants don't matter. So we can also ignore the 3 here. So we're ignoring the lower degree terms, n to the 1 and n to the 0. And we can ignore the constant here. So this would just be O(n) squared. So now, oh, wait. Okay. Okay, so with this code snippet here, I want you guys to determine the complexity of this code in terms of m and n. So I'll give you guys a few minutes to try this, and then. Okay, so can anyone tell me what the time complexity of this would be? Yeah? Correct. So the time complexity is O and m squared. So the reason why this is an m squared is because in our final for loop, you look at, it says in k equals j, then our stopping index is when k is less than m, and we increase k by 1. So when we start k equals j, our initial value of j is j equals 0. So k would go from, when j is equal to 0, okay, yeah. When k is equal to 0, it will go to k equals m minus 1. Similarly, when j is equal to 1, it will start with k equals 1, and it will go to m minus 1. So this will have m operations in it. This would have m minus 1. And when j is equal to 2, k equals to 2, goes to m minus 1. This will have n minus 2. And it decreases by 1 each time. So in total, we're doing m plus m minus 1 plus m minus 2 plus dot 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 plus 1 operations within the last 2 loops. So can anyone tell me what the summation of this would be? I think you said it, m times m plus 1 over 2. So this is the amount of operations the last 2 for loops do. Now, our first for loop just iterates from I equals 0 to n. So it doesn't hold anything for the first. It doesn't affect the other 2 for loops like the second for loop does to the third one, because k equals to j. So the third loop is dependent on the second for the values, but the first one is completely independent from the other 2. So this will just run n times, from 0 to n minus 1. So in total, we're doing n times m plus 1 over 2 operations. O is O. And this would be equivalent to O of nm squared plus nm over 2. And as stated prior with the question before this, we can ignore lower degree terms. So we can ignore this. And constants don't matter. So the 1/2, we can completely ignore this. So this would just be O of nm squared. Does anyone have any questions about how I got? Yeah? Because as n goes into, so example, let's say we have 2n and 3n. Let's say we have 2n and 3n. As n grows larger, so when n goes to infinity, these values would, the constant won't affect it by much. But when we have something like n squared and n squared goes much larger than n does in polynomial terms. And similarly, I'm not sure if you guys covered this yet, log n is much faster than n. In terms of same degrees, we only care about the upper and lower bound with a constant. The definition, I believe, was f of x is less than or equal to c of g of x. So when we have 2n and 3n, we could just keep it as, we know we can use the same value. We can get an upper bound with n. So we can get this to be cn and this to be greater than cn. We can find a c that makes both of these hold. But with n squared, we can't, because n squared is much greater than n. So yeah, I don't think you guys need to know this part, so that's fine. Any other questions? No? Okay, so I think that wraps it up. Oh wait, yeah, my bad. Okay, yeah, my bad, guys. This is a quick thing. So with linked lists, so when we do time operations, inserting and deleting at the head of the linked list is O1, since it's just one singular operation. At a specific node, it will be On, and the reason why it will be On is because we have to assume worst case. We have to assume it will reach until, let's say, so we have to assume it reaches until the last node. In that case, we traverse the entire list. So n is the size of the list. So the worst case is we traverse the entire list and we insert and delete it. Same thing as searching and traversing. Reach the last node is our worst case. In that case, it will be On. And yeah, I think that will be it. Thank you so much for attending. If you have any questions, we will still be here. And yeah, good luck on your midterms.